Welcome to Theory of Matrices. I'm Robert Gardner, Dr. Bob, and we're going to go through some notes for Math 5090, ETSU's Theory of Matrices class, graduate level class, building largely on sophomore linear algebra. So let's first just run through very brief chapter one. Chapter one is basic vector and matrix structure and notation. And what we'll be doing in this class is largely dealing with vectors and matrices with real entries. I don't got a problem with dealing with complex numbers. In fact, that's what I'm trained to do. My PhD stuff was in complex numbers, and there's a lot of useful stuff happens with complex numbers. This course, using a book out of a series kind of aimed at statistics applications, largely sticks with real numbers, not exclusively, but largely. In a more theoretical class, we might actually take the entries from an arbitrary field. But the field, to throw around some algebra terminology, but the field we'll use is the field of the real numbers versus the field of the complex numbers, or something somewhat more abstract. The terminology we use will largely overlap with sophomore level linear algebra, Math 2010 here at ETSU. Our notation is going to be a little bit different. One thing, we won't distinguish between scalars and vectors as conscientiously as we would in a sophomore linear algebra class. The difference should be clear from the context, though I'll still probably make a big deal out of it, at least in the beginning. Our first definition is an n vector. Take n to be a natural number, 1, 2, 3, etc., positive integer. An n vector is an n tuple of real numbers. The collection of all n vectors make up n-dimensional real space, denoted Rn. Your sophomore level linear algebra class was probably largely devoted to Rn. You might have brushed on Cn, the complex numbers, taking n tuples, n vectors of complex numbers. Probably not in the sophomore level linear algebra class because you got so much other stuff to do. There's some definite advantages to allowing the complex numbers to come in, especially when you start looking for eigenvalues. Eigenvalues are zeros of polynomials, and sometimes you got to deal with the complex numbers to have all of those eigenvalues and all those zeros of polynomials present. Okay, we're going to denote n vectors this way or that, so we're not quite as conscientious in terms of taking transposes and so forth as you might have been in linear algebra, hopefully so, and good for you. We'll define a column vector x to have entries x1 through x sub n, or maybe the row vector x to have entries x1 through x sub n. Doesn't much matter as long as within one particular setting or one particular question, we consistently use columns or consistently use rows. The only time it'll really matter is when we multiply vectors by matrices, and then the row times column matrix multiplication thing will have to hold, and likely we'll have to use column vectors at that stage. We're not using special symbols. We just wrote vector x in both cases, so we're not using special symbols like putting a little arrow over the x, or using a boldface font. That's quite common in math and physics to use boldface fonts to represent vectors. We will depend on the context to distinguish between vectors and scalars. All right, you can't add scalars to vectors, for example. You can't multiply vectors together. There's dot product, but that was something different. We're constrained by what we can do to vectors to distinguish whether we're dealing with a vector or a scalar. Still, as commented, I'll probably make a bit of a big deal out of it, maybe too much so, at least in the beginning. A matrix. Matrix is a rectangular array of numbers. An n by m matrix is a matrix with n rows and m columns. Following the book's notation here, notice the n comes first and the m comes second. They're dummy variables, nobody cares. But it's quite possible in your previous experience, you more often talked about m by n matrices instead of n by m matrices. So just keep an eye on the fact that n represents the number of rows and m represents the number of columns in our conversation with n by m matrices. They've interchanged the roles of m and n from what I'm used to from my many years of sophomore linear algebra. But we're letting matrix A, of course, we'll usually denote, you're familiar with this, a matrix with a capital letter. It's entries with double subscripted corresponding lowercase letters. And the indices indicate the location. So if I want the 2, 1 entry of matrix A, it's in the second row and the first column versus say the 1, 2 entry, which is in the first row and the second column. So that's how the indices indicate location in these matrices. And we could take the set of all n by m matrices with real entries and denote that as R n by m. When you see these R's with what appear to be exponents, you're probably thinking vector space. Yeah. We could make a vector space out of all n by m matrices, just as we can make vector spaces out of all n vectors. More on vector spaces later, but we could make vector spaces out of these matrices as well. And I think that's what motivates these guys to use that notation. In fact, those vector spaces would be isomorphic to the vector space R in M, the product n times m. The dimension would be n times m. In this course, vectors and matrices, they're all finite. I wouldn't say there's no such thing as infinite vectors and there's no such thing as infinite matrices. Some of the most useful applications of vectors involve vectors from infinite dimensional vector spaces. And the linear operators on them, or linear transformations, are represented by infinite matrices. Not our problem though, not standard topic for theory of matrices classes. Yeah, that's because as soon as you make a transition from the finite to the infinite, then you got to worry about a bunch of analysis stuff. So now you got to worry about convergence and divergence every time I take a matrix product or a dot product with vectors. It becomes way more analytic if we go and allow infinite matrices and infinite vectors. There's a whole area of math devoted largely to that. Functional analysis, we have a class called Fundamentals of Functional Analysis, Math 5740, that will deal with these concepts in an analysis setting. When you hear infinite, it's going to have to be something that analysis deals with. As I mentioned, this book comes out of a series of Springer Verlag books aimed at statistics and applied statistics in particular. Pages 7 and 8 of the textbook, they describe ways that matrices and vectors can be used to represent data. We'll certainly call attention to some of the statistics applications, but in our limited time, it's mostly we're here for the matrices and the properties of vector spaces and the interaction of matrices and vector spaces and eigenvalues. But some of the applications related to statistics will encounter that as well. So there's chapter 1. We'll move on to chapter 2, which will take significantly more time for us to cover. I'll see you then.